So we need to kick it into gear a little bit. A little bit, yeah. We're supposed to be on chapter 4 now. We got like 2 more sections to cover in chapter 3. So, yeah. We spent a little too much time on this, and so I still do want to talk about a couple more things about this section 3.4, and then we'll try to see if we can fly through the rest of the chapter. But for today, we left off with looking at a matrix, an elementary matrix that involved a row switch. So if I want to talk about a row switch, for example, when we're switching rows, we're that idea of switching a row is called a permutation. Well, switching a row is an elementary row operation, and there might be some cases where we need to switch more than one time. And so it turned out that the product of those switches is called a permutation matrix. So a permutation matrix, it's not defined here. Permutation, let's put it over here. Permutation matrix is a product of row switches. So if we just have to do one row switch, then that's fine. But in some cases, we might have to do multiple row switches. And so that multiple row switch will involve taking the product of your matrices. And so that's going to be denoted as a permutation matrix. And a theorem that we're not going to prove says that, we won't be proving a lot of theorems, but a theorem that we won't prove today is that the inverse of that matrix is actually the transpose of a permutation matrix. Yeah? Yes. Yep, we're 2.5 minutes or almost 3 minutes in. So yes. Okay, so that's the whole idea behind the permutation. And so if we're trying to find an LU decomposition and our top left-hand corner of the matrix is 0, then we would need to swap. We would need to swap rows, and so that row swap will allow us to get this set up so that we can do the row reduction business. So let's do an example first, and then we'll see if we can follow through with the rest of this business. All right. Here's my matrix. I have a 0 in the upper left-hand corner, and so I can't move from here until I do a row swap. So let's do a row swap. Let's switch row 1 and row 2. And I want to keep in mind what that elementary matrix operation is for later on. And so the row swap is going to give me a -1, 1, 1, 2 for the top row, and then 0, -1, 1, 3. And then I have a 0, 1, -1, 1, and a 0, 0, 1, 1. No, that was number 24 or something like that, and then there's a dot, so ignore that. Okay, so we have done one elementary row operation, and if we try to get rid of, we're going to do another row operation here, and then we're going to run into another issue where we're going to need another row swap. And so what I'm going to do is I'm going to do this operation, and I'm going to scratch it out, but we'll see how this is going to work out. I suppose you should do that on your paper too, to physically scratch it out. Well, not scratch it out, whatever. Okay, so I'm going to take row 2 and add it to row 3, and then I'll replace row 3 by that, right? So row 1 stays the same, row 2 stays the same, and row 3 is going to be 0. Now if I add the second one, that's another 0. And then 3 plus 1 is 4. So it looks like at this point, this is not the row echelon form that I want, right? And so I needed to have switched row 3 and row 4 first. So this is where I'm going to backtrack a little bit. And what I'm going to do at this point is say that that's not what I wanted to do just yet, because the 0 is kind of, I'm not in row echelon form. So I would switch row 3 and row 4 first. So I'd come back here and do another row switch. So I have negative 1, 1, 1, 2, 0, minus 1, 1, 3, 0, 1, 0, 0, 1, 1, and then 0, 1, minus 1, 1. Now I'll do that row operation where I'll try to wipe out the leading term in row 4. So I'll take row 2 and then add it to row 4. So that is going to leave everything except row 4 the same. So this will give me 0, 0, 0, and then the 3 and 1 is a 4. So this is a 0. So now I have my upper triangular matrix, and I should have enough information to find my lower triangular matrix as well. But before I did any of that, I did two things. I did two row operations that involve switches. Okay? So what I really did here is I have my A. First, I did a row operation, let's call this E1, where I switch row 1 and row 2. And then I have this other row operation, we'll call it E2, where I switch row 3 and row 4. After that, I get this breakdown. I have my lower triangular matrix, or I can figure out what my lower triangular matrix is, and my upper triangular matrix is this. So let's first find our lower triangular matrix. So L is equal to, now remember this is a unit lower triangular matrix. So we have 1s in the diagonal. And then we're going to have those coefficients of those row operations that we did. Now, in this particular case, we only did one non-switching row operation, so we're really only going to have one non-zero in this lower triangular. Where is that going to be? So from my row 2, I added it to row 4. So what if this is a what by what position? 2 by 4? Row 4, column 2, 4 by 2. So it's in the 4th row that changed, and it was from the 2nd column. So it's a 4 by 2, and what number is this going to be? 1? Negative 1. So remember that this number over here, whoops, not that one. This number over here, because we crossed that one out, right? What we want is the opposite of that number, and that number that changed is a position that we're going to want to change. And so the opposite of this number is negative 1. So there's a negative 1 here, and everything else is 0. Because we only had to do one of those row changes. So this is our lower triangular matrix. Okay? Yes? Okay. So what I needed to do is I needed to make one of these things 0. And I want to know which spot did I make 0. So this is the spot that I'm looking at to make it disappear, make it into a 0. So for my lower triangular matrix, that's the spot that I would be focusing on. And what number do I put there? The number I put there is the negative of that coefficient that I multiply one of the rows by to eliminate that. So this 1 will become a negative 1, and it will be in this spot right here. R4 was the one that was replaced. At least that's how I do it. I don't know if, I think the book does it kind of like this way. If you go on YouTube, then they have some other way of doing things or whatever. But in any case, we should get the same answer. Okay, so we're not quite done yet. We have L and we have U. Now, we're going to figure out what are those two switches that we did. We have to account for that so that A is going to equal to this decomposition. So the E2 matrix is switching rows 3 and 4. So we start off with the identity matrix, and then we switch the 3rd and 4th rows of the identity matrix. So that's E2. E1 is switching the 1st row and the 2nd row. So we start off with the identity matrix, and we'll switch the 1st and 2nd rows, and then we'll keep everything else the same. So each of these would be considered an elementary matrix. And what we're going to do is we're going to find P, the permutation matrix, just by multiplying or combining these two elementary row operations. So P is equal to E2 times E1, which is equal to, now we got to do this multiplication, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Well, did you see a pattern? Yeah, if you have row 1, row 2, row 3, or row 4 you're switching, then that's okay. You could just, but if you have row 1, row 2, and then you, for some reason, you wanted to do row 2, row 3, then there's going to be some issue there, so you should multiply that to make sure. Okay, since these did not conflict, these row switches didn't conflict with one another, then it turns out that our permutation matrix, or we want the inverse of this. It turns out that the inverse of this will be itself again. But because of that theorem, in case the inverse was not itself again, all we have to do is take the transpose. So the transpose of this matrix is going to be itself, because it looks like if I switch everything across a diagonal, I get the exact same matrix. So that's my PT. And I think I would be done at this point. And we can rewrite our A as a product of matrices. First, permutation matrix. Oops. And then my L matrix that we just found. And the upper triangular. And that's it. We're done.
When you were doing this procedure, you found that you used your permutation after you'd already done a non-permutation. So you always have to backtrack, is that right?
Well, that's what I did. You can work around that by doing this and then just making sure that this elementary row operation came in between, and then you would do that permutation. And yes, so the answer to your right. And then do that switch later if you want. But I think it's better to just backtrack. When you get to here and you think, oh, crap, I need to switch first. And so you would go and do the switch and then redo that operation. It would just make it cleaner to follow. So this is our PT, this is our L, and this is our U. I hope so. Did you put it in there?
I didn't put it in.
Or just multiplied in your head?
No, but
Oh.
yesterday.
Oh, okay. Oh, cool. Yeah, so if I were to take this, I don't want to, but if I were to take this and then put it in Mathematica and multiply it all out, I should get the original A matrix back. Okay? All right, questions?
So you can solve this the same way we solved the LU, that is, you solve.
Yeah, so if this was a system,
If you had a bunch of P's,
yeah, we would just have to deal with the P. Well, you combine all the P's together into one P.
so you say PTZ is P, and then LY is C, and then UX is Y. Right?
Yeah,
Sort of peeling it inside out.
yeah. I don't know what the permutation will do to the solution. No, because these are all just ones. They have ones.
So you just transpose it and multiply.
Yeah. I think an issue with that is that if we're going to go back and do the systems, which is what this is all based on, if we're going to do the systems of solution, this thing might not have, it might be one of those systems where it's inconsistent, or it would have infinitely many values, because we're not assuming, this is for any square matrix now. It's not necessarily I was going to say rank n, but it might not have it might have infinite number of solutions and stuff like that. So you might have some issues. Okay. I'd like to be done with this, but there's one more thing I really want to show you. And so I'll show you. Maybe I'll talk about it, and then maybe work an example out a little bit later on. So what we've been working on is an LU factorization. And so there's many other types of factorizations that exist. But another one that does exist is an LDU factorization, where, as they explain here, L is that unit lower triangular that we've been working on, and then the D, and then U is a unit upper triangular, and now D is just a diagonal matrix. So that's because L is going to be is already a unit upper triangular. The U is going to be broken up into a D and a U. The
almost the scalar to make it not unit.
Yeah. What? Huh? Okay, wait. Let me just take this. Okay, first of all, did you guys understand what Becca just said? Okay, she said in the LDU, let's just say you have a matrix A, and we talked about an LU decomposition, right? Where L is a unit, and maybe we should put a subscript for 1 here that says it's a unit lower triangular. And U is just an upper triangular, not necessarily a unit upper triangular. So what they're saying here is the LDU factorization is that A can now be broken up into a lower unit triangular times a diagonal matrix with just numbers in the diagonal and zeros everywhere else. And then the unit, and then the upper triangular is now a unit upper triangular. Okay? And so, because L is already a unit lower triangular, it looks like the main task is just to break up the U, the regular upper triangular, into a diagonal and a unit upper triangular. D is going to look like a diagonal matrix. No. So these would have 1s in the diagonal and zeros, and then we'll have a lower triangular with a unit. This would be just a diagonal and zeros everywhere else. And then this would be 1s in the diagonal and something up here and zeros in the lower part. Okay? And without doing much work, we can probably see that the diagonal from the upper triangular matrix that we had would go into this diagonal on its own, and then that would just make these into 1s. But that's probably something that you should explore and examine and stuff. So this is from your book on the problems on page 197.
You don't just make a diagonal into 1s, you have to scale the whole world.
Yeah, I think it might actually work out where it's just going to be 1s.
Yeah, but you have to change the things in the rest of
These things would scale?
Yeah, because, I mean, look at the way everything on the diagonal is multiplying 1
Right.
on the right.
Right.
So you've gotta
So everything in there would scale. Yeah. So they won't be exactly the same. So like if whatever numbers are here for this upper triangular will get scaled over here for the unit upper triangular. All right, so that'll be on your own. You can look at that. And I brought it up because it might be on the test. So. All right, let's shift now to 3.5 subspaces. And it's kind of hard to talk about subspaces when we don't have the basic foundation about vector spaces in general. So what they did here is they tried to simplify the discussion by just saying a subspace of Rn. Instead of just in general, we should be looking at a vector field, and then a subspace of a vector field has certain properties. But here we'll just stick with Rn, and for visualization purposes, we'll take a look at R2 and R3. But technically, this could live in Rn, like R5 if you want, and this technically can also live in complex vectors, using complex vectors of like size whatever. So it could be in Cn as well. And for that matter, it could be in our finite fields. So let's start off with a definition of a subspace. So the idea here is that we're looking at Rn, R2 or R3, and we're going to define a subspace. So a subspace of Rn is any collection S of vectors in Rn such that it has to satisfy three things. One, it has to contain the zero vector. Two, if you have vectors in S, then any addition of those vectors would still be in S. And three, any vector in S can be scaled into any other vector in that subspace. I don't know if that made any sense, but let's see if we can visualize this. Well, before we try to visualize it, the conditions 2 and 3 can actually be combined into one condition where we're taking a look at a scalar multiple of those vectors, or a linear combination of those vectors. So any vector you have in a collection of sets there, we can take a look at any linear combination. What? What? Okay. Don't worry about it. Let's take R2 and R3 separately and take a look at the different kinds of subspaces that might exist there. So let's go to R2 first. And let me show you a subspace at R2. And this is a subspace in any vector space that will exist. Let's say if we have the zero vector, then this is a subspace of R2. Okay? It's a boring subspace, but it still satisfies these conditions. First, 0 is in there. So in this case, in R2, it would be 0, 0. Yeah. So the subspace containing the zero vector is the zero vector is a subspace. So 0's in it, clearly. 0's in S. And so if you have two vectors in there, we really only have one, but if you add those two vectors, 0 plus 0, it's still going to be 0. Let's just write it down, just to be technical. So let's say this is our S. So 0 is an S, so that the first one is satisfied. The second one, if you have two vectors in S, then the sum of those two vectors will still be in S. So let's pick two vectors that are in S, like 0 and 0. And if you add that, you get 0. And that is, this little E symbol, by the way, is an element in. So that's an element in S, so that works out also because it's closed under addition. And if I take any scalar, like 15 or negative 12 or something, and multiply that by the vector, I keep putting sigmas, multiply that by the vector 0, this is still going to be the vector 0, which is in S. So it satisfies those three conditions. So my vector subspace 0 is, well, my subspace 0 is a vector space, or it's a subspace, whatever. All right, now let me come up with another vector. What if I just have one vector, 1, 1? Then I can also show that this is a subspace, or the span of this is a subspace. Is it? No, what do I need in there? I need the 0, 0 vector, right? So now I have two vectors. Now, is this a subspace? Let's see. 0 is in S. If we add 0 plus 1, 1, this is also going to be in S. And if I have any number and I multiply that by 1, 1, is this going to be in S? Like if I had 5? So this is not a subspace. Right? That's too bad. What can I do to make it a subspace? Yeah?
Well, I was wondering why we use oh, I see.
So what can we do to make this a subspace?
Explain about your check mark and run, too.
Okay.
Because you were lucky and you selected two that happened to work. But
Right.
selection didn't work.
So let's select something different that wouldn't work. What two vectors can I add that wouldn't work? 1, 1, and 1, 1. So that check mark wasn't really a good check mark, so that didn't work. So this is not an S. We're checking to see if this is a subspace. Because if according to this definition, if I take any two vectors, including repeats, and if I add them, I should still get a vector in that space.
Oh, okay. I thought that was the situation of u being 0, 0, u being 1, 1, and u just being
Well, yeah, so that would be the same. If I let u equal to 1, 1 and v equal to 1, 1, It's kind of like the same business. The thing is that I can let U and V whatever I want, including repeats. So, this is not a subspace. If we try to visualize this, because we can in 2 dimensions, if we try to visualize this, we're looking at a vector 0, 0, and then the vector 1, 1 that looks like this. Now, if it's supposed to be closed under addition and scalar multiplication, what types of vectors am I going to be allowed to put into, what types of vectors do I need? And I'll underline some of these things. What types of vectors do I need so that I can get a subspace? I can account for all those vectors that were not in S here. What other vectors do I need to add on to my S? Jamie? And N. So that's what you guys were going to say? So if I change my vector, if I change my S into any vector XX, or X can be any real number, then would that work as a subspace? Let's see. So is a 0 vector in here? Yes, because if X is equal to 0, then I get 0, 0. So this is a check. Now if I take any 2 vectors, let's call them XX. And so I want something different, like YY. This would be X plus Y, X plus Y. Is this a vector in S? The condition is that those 2 numbers have to be the same, right? So if the first one is X plus Y, the second one is X plus Y, then this will work. So this is, yes, in fact, in S. So this is another check. Now, if I have a scalar like 15 or negative 10, and if I multiply that by some random vector in my set, I will have alpha X and alpha X. And is this in S? So this is an S, so that works out. So now this is a subspace. Probably a little bit different. Is there another way to represent this S? Can you see another way to represent this S? What am I looking at for this S? So this is XX for X, any real number. I can have positive numbers, I can have 0, I can have negative numbers. So what is it that I'm actually looking at when I look at this subspace? It's a line. It's a subset of R2. It's what? It's a subspace of R2. It is a line. Do you see that line? So this is really a line, or the line X is equal to Y, or Y is equal to X. That's just another way to express that. No. You can think about it as a parameterized line, but the point is that it is a line. Victor asked, is this a special case, and I said no. Why did I say no? You see a lot of this? Well, a line seems like it would be a good candidate for a subspace in R2. You have something in 2 dimensions, and it seems like a line would be a subspace. Okay? Let's think of another one in R2. When I say S is a set, they say it's a set of vectors in here to account for infinitely many elements in that vector. I'm just going to use this notation. Collection of vectors, yeah. So, is this a subspace? I have X and 2X. Is this subspace? Well, let's check. Is 0 in this set? So when X is equal to 0, this works. X and 2X. What if we added another vector Y and 2Y? Then we get X plus Y, 2X plus 2Y. Is this, can I write that in this form? Something, 2 times something. If you factor out a 2, that'll work out. So this is an S, so that's good. And then the third one, if I multiply this by alpha, I'm going to get alpha times X and then 2 alpha times X. Is this still is this still in the set? If you look at alpha times X as X, right? It's still in the set. So this is some number, and this is 2 times that number. So this is still an S. So this is a subspace. Yeah. So the S in this case can be described as a line what? Y is equal to 2x. Right? So that's another subspace. So are all lines subspaces? Okay. So it turns out that all lines that pass through the origin are subspaces. Of R2. And then if you have a line that doesn't pass through the origin, then it's no longer a subspace. Okay? So in R2, lines that go through the origin is a subspace. Well, I suppose we can take this and generalize this too. Turns out that all lines through if we have a line that passes through the origin in 3 dimensions, that's also a subspace. This time in R3. Okay? In fact, you can generalize this to any line in n dimension. So if you run into a line that doesn't pass through the origin, then it's no longer a subspace. Okay, is that cool? Yes?
So it's absolutely necessary that it goes through.
Yes. It absolutely is necessary that it goes through the origin because of the first condition.
But just because it does doesn't mean the other ones follow.
Just because you have something that goes through the origin? Yeah, it depends on how you define your subspace. We care about subspaces because what we want to do is we want to take a look at the mathematical structure of our solution set. When we have a system of linear equations, for example, we have to know in which space are we looking at our solution sets to be in. Okay. All lines through any zero vector in any dimension is a subspace of Rn, whatever dimension that is. These are all quotes. Okay. So this is all kind of being spanned by one vector, but we could take a look at things that are spanned by two vectors. So do you see that this conditions 2 and 3 kind of bring out the idea of spanning? Spanning is like a linear combination. It's addition and a scalar multiplication of vectors. And if you combine these 2 points over here, 2 and 3, you're really looking at a linear combination of those vectors. So let's go back to R2. What if you have S is equal to the span? Span means linear combination of 2 vectors now. So that means this is going to be any linear combination, which means a scalar times the first vector plus another scalar times the second vector. So the question is this set a subspace of R2? Well, we have to take a look at the whole thing because when we're taking a look at the span of something, we have to consider all possible linear combinations. And so if I want to show that this is a subspace, I would check to see if the 0 vector is in the subspace. And is it? I want to check if S is the subspace of R2. So is a 0 vector in the subspace? How am I going to get the 0 vector in the subspace? Alpha and beta are equal to 0, and then that's just going to be 0. So that works out. 2. Now, if I get two random vectors here, and by random I mean I'm going to have to randomize alpha and beta. So vector 1, I guess I call it U, equals alpha 1 times 1, 1 plus beta 1 times 1, 2. And then V is a different alpha, so I'll call it alpha 2. If I add those two vectors, the question is, am I still going to be in the subspace? So U plus V is equal to, can I just simplify it? So U, the alpha 1 and alpha 2 can factor out with the vector 1, 1. So alpha 1 plus alpha 2, 1, 1 plus beta 1 plus beta 2, 1, 2. And this looks like it's in the same form, right? Something times 1, 1 plus something times 1, 2. And these are the two somethings, and they're both real numbers. So this is also an S. And the same goes for a scalar multiple. So I used alpha and beta, so I'll use another scalar. I need another Greek letter. Let's use gamma times U. So this is gamma times alpha 1, 1, 1 plus beta 1, 1, 2. I guess I should have just used regular parentheses. So this is gamma alpha 1 and gamma beta 1. And this is again in the same form as all those elements, so this is also an S. Okay? So what does this look like in R2? A plane. So it's two different vectors, right? And any linear combination of those two vectors turns out so these are the two vectors, and if I take the scalar multiple and sum of these two vectors, or any linear combination of these two vectors, I can essentially get every single point on the plane. So what can you say S is equal to? S is not only a subspace, but it actually is equal to R2. So we showed that it is a subspace, but it actually is equal to the whole thing. Does that make sense? So R2 is a subspace of itself. Okay? In fact, in this example, if we have any two linearly independent vectors, as long as those two vectors are linearly independent, then the span of those two vectors will end up spanning all of R2. and therefore is a subspace. Okay, feel like I've lost half the class now. No, I'm just, in general, the eyes and facial expressions and stuff.
Why were we showing like R2 and subspace R2?
Because now we've shown that there's how many possible subspaces of R2 do we have, and how do they look like? If I'm just looking at R2, we have an infinite number of them, but what kinds of subspaces do they look like? So they're either a zero-dimensional subspace. So our conclusion here for R2, let's conclude this already. R2. So the possible subspace, if you have the zero vector, that's a zero-dimensional subspace of R2. It just involves a point. If you have a line that goes through the origin, I guess that would also include the vertical line, right? So if you have any line that passes through the origin, this is also a subspace. And all of R2 is our third possible subspace. So we have a zero-dimensional subspace, a one-dimensional subspace, or a two-dimensional subspace. And those are the only possible subspaces we have for R2. Yes. So a subspace is a degree or a dimension equal to or below the vector space that you're looking at. Okay? All right. So we can do the same song and dance in R3, or I can just tell you what those possibilities are. So I think I'm just going to tell you what the possibilities are for R3. In R3, the possible zero-dimensional subspace this is S/space, is going to be the zero vector. That's always going to be a subspace. A one-dimensional subspace. And for this, I'll just describe it as I can describe it as a span, or I can just describe it as a vector, or a geometric object. It's a line going through the origin. And so example would be S is equal to the span of one vector. If I just have one vector, the point is 0, 0, or 0, 0, 0, and the vector u would be the direction. And then I would have multiply that direction by t. I would have the span of that. Our two-dimensional subspace would be a plane through origin, and the span, we can think about that as a span of two vectors, u and v, as long as the vectors are linearly independent. That's my shorthand. What happens if you have two vectors in the span of something, but they're linearly dependent? What do you actually have? No. If I have two three-dimensional vectors, like 1, 1, 1, and 2, 2, 2, and they happen to be linearly dependent, what do I really have here? It's just a line. It's just in one dimension, right? So that's why I want this to be linearly independent, to be able to span a plane, something in 2 dimensions. And if I happen to have a span of 3 linearly independent vectors in R3, you get all of R3. Origin. Can't you tell?
Yes.
A one-dimensional subspace. Yeah, so the S slash, so these are your 4 possible subspaces in R3 now. You either have 0, just the origin, you have a line passing through the origin, you have a plane passing through the origin, or it's all of R3. Okay? So all those other planes that don't pass through the origin cannot be considered subspaces because they don't have 0, 0 as part of their set. Okay? All right, so here, they consider this a theorem. I kind of didn't consider it a theorem because by the definition of the second and third criteria for subspaces, it was addition and a scalar multiplication, and so that just got combined. I don't know if that was worth a theorem, but in the book they call it a theorem. So if you have k vectors in Rn, the span of those k vectors is considered a subspace in Rn. So the span, remember, is a linear combination alpha 1 v1 plus alpha 2 v2 plus dot 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 plus alpha k vk. So that kind of follows from the definition of subspace. Now the question here I would have, and this is kind of something I referred to earlier already, is the span of these vectors is this a k-dimensional subspace? What would you say? So k has to be less than Rn. So Justin's comment about the dimension has to be less than the dimension of the original space, less than or equal to. So k is less than n. Okay, we're given that. If I take the span of all those vectors, is this going to be a k-dimensional subspace? Not necessarily, and why would it not be? So if they're linearly dependent, right, we can eliminate some of those vectors because they would be linear combinations of a few other vectors. Not necessarily, and it would be a no if it was linearly independent. It would not be a k-dimensional, yes, dependent. It would not be a k-dimensional subspace if this vector, this set of vectors, is linearly dependent. So the question is that, is a span a k-dimensional subspace? The answer is no, not necessarily. And it would be no, definitely no, is if the set of vectors is linearly dependent. So if it was linearly dependent, then we can eliminate one, maybe two of these vectors, and then so it would be a smaller dimension than originally thought. Just like in 3D, if I have 1, 1, 1 and 2, 2, 2, and I take the span of that, that's not a two-dimensional subspace. That's just a line. So it's just a one-dimensional subspace. But if they're all linearly independent, then you'll have a k-dimensional vector space, subspace. All right, one more piece of information. Whoops. So this is something that we're going to dive into next time, the row and column space of a matrix. A matrix is really a collection of vectors, whether you look at the columns as vectors or you look at the row as vectors. It's a collection of vectors. And in either case, we could take a look at the row space of a matrix by looking at the rows of those of that matrix, or we can look at the column space of that matrix by looking at the columns of those matrices. And then you can, from there, create a subspace of either Rn or Rm if you don't have a square matrix. Okay? So we're going to start off with this definition next time, and we're going to see if we can go kind of fast because we're a little behind here. You guys will have a quiz on Wednesday. The quiz will be on LU decomposition. All right. Goodbye.